So very briefly, I will tell you how this is possible even today. You don't need to be Vahan, Shengta, or me to do this work. In fact, you can go to Amazon Bracket and do it today. So Amazon Bracket is a platform that is open to the public. It's an AWS service, which means anyone who has an AWS account can use it. The philosophy of Amazon Bracket is that we are accelerating quantum computing research. I personally consider that message close to my heart. I think this is the right message at this time in this field, and this is what this platform is built for. So the idea is that you can do all these steps within the same framework. You can build your use cases, you can build your circuits or your quantum programs. You can test them on simulators. Some of them are attached to the client-side software. Some of them are attached to AWS instances that are managed for you. So you pay only for the compute. You don't have to manage them. You can run them on the devices attached to the Amazon Bracket service, and you can analyze the results. All of this are in managed environments. So the idea is that if you don't want to deal with the latest version of Qiskit and how to actually install with the other dependencies, we have that in a notebook. It's a bit of a manual labor on our end to keep them updated, but they're always there. So feel free to use them. So these are the current devices or categories of devices available on Amazon Bracket. We have devices that accept quantum circuits as a paradigm. So ion trap-based devices, superconducting-based devices from Rigetti and IQM, and of course the ion traps are from IonQ. And we have the Quera device, Aquila, which accepts this analog program. Very briefly, I believe you are more familiar with this than maybe 3 days ago, but I will go through currently a couple of things, not a few knobs that can be changed, but all of this is enough to do the work, to repeat the work that Vahan just showed you, or go beyond. So there's a driving term, there's an interaction term. The driving term starts with this omega term. So it's omega divided by t as the amplitude of the drive. There's an additional phase you can tune. So that allows you to switch between x and y or anywhere in between. And there's a detuning, which acts as a global z field, essentially, on these qubits. The interaction is exclusively tuned by the distances of the atoms. And you can imagine that this is a large limitation. But in fact, that's the closest we can get to the physical reality that's running on the device. And so we decided to not abstract away from that. That's probably not what I wanted to show. Let's see if I can get back to my screen. There we go. So the interactions are tuned by the distances. And so these are the parameters that need to be put together in a program so that it can be run on the device. So an analog program is very simply absolutely on the lowest level of programmability, and for me that's actually a pro. I'm happy that I can get close to a physical experiment. So you start with defining the atom arrangement. You define the sites as XY coordinates. We use standard SI units just because that's easy to remember. You don't have to figure out if that's like micrometers or nanometers. Just tell you it's always meters. It's a bit cumbersome to look at this 1e-6 appendages every time that you run the program, but you don't have to. You can write your utilities. The idea is that on this level, it's unambiguous what you're constructing, so you don't have to second guess yourself. And of course, you can build your own utilities to make your life easy. So the atom arrangement is a bunch of sites, XY coordinates. You can choose to leave some of the sites empty. That currently is not the most useful thing to do, but maybe in the future this will come handy. And then the second piece is the Hamiltonian. The driving field I already spoke about. I showed you the formula. It has the amplitude, the detuning, and the phase that you define as time series. And then there's an experimental capability, which you already heard about. It's the local detuning field, which has a magnitude piece that comes with the time series and the pattern. So you can apply a pattern, which is a static pattern. That pattern gets multiplied with the time series, and it's applied during the same period of time when the drive is applied. So experimental capabilities, it's not just a story, it's actually there. You can go to the page, you can click on Bracket Direct, and you can scroll down to the experimental capabilities. If this is a new account you set up, then all of these are not enabled. We want to have those guardrails in place. But if you choose to, click on the buttons of get access, you fill out the form, and after that, you get access to these things. As easy as that. No strings attached, same thing as always. We have very strict guidelines on not looking at what you're running. It's a service, same as any other service at AWS. So let's do a very simple demo, but not really a demo, just walking through how simple it is to construct. This is, again, low level. On the box, on the top, you construct the atom arrangement. We have the Python libraries ready for you, so it's very simple. You import from bracket.ahs, and then you construct the register by adding XY coordinates to it. It's not rocket science. The reason I'm showing it is that the only thing you need to feed it yourself is this my coordinate list. And that is literally a list of XY numbers. So you can go really close to what the device is doing. Same thing here. The Hamiltonian is constructed out of 4 lists. You tell the times, the amplitudes, the detuning, the phases, and then that constructs it for you. And after that, you put the 2 things together, you get an AHS program, which you can run. You can run it in 2 different ways, at least. You can run on client side using a software which is not too powerful. It can simulate up to 12, maybe 15 qubits. If you're happy with that, you can scale it up, and you can run it on Aquila. It's a bit more cumbersome. There's a discretized step in the middle, which means that you need to prepare the program to be close to what the device is actually accepting. You can check that it's close enough to what you wanted. There's a bit of a back and forth there. But after that, you just run, and you get the results. The results look like this. Again, very raw. The order of these bits, or characters, is exactly the same order in which you added the atoms to the atom arrangement. So you need to do quite a bit of post-processing. But to me, that's quite exciting. Like, I want to do that. I want to do the analysis myself. So here it is. So it tells you if it's on a ground, Rydberg, or an empty site. So once in a while, an atom is missing. We decided to not throw them out. But it's there. You can choose to post-select on that. And so that's, again, on you to do the analysis. You can plot it like that, and that's it. I think that's the final slide. So thank you for the attention. This is all the folks who are involved.
There's no question using bracket. That's what I get.
I can ask one, but I don't need the mic. So how much does it cost?
How much is the... So a single experiment, if you want to do 1 run, that's a single task. This is how we measure it. A task is 30 cents. A single task costs 30 cents. And depending on how many shots you have in the task, each shot is 1 cent. So you can run a 100-shot experiment for $1.30. That's usually enough to convince yourself that what you're trying to do makes sense. If you're willing to pay that out of pocket, then you can write a research grant asking for more money, and then you will get the money on the account, so you can spend it. That's also possible, but this is just another device. Similar to a synchrotron, similar to a telescope, you can write the access for hardware part of the grant, and you can get the money for it. From NSF, I meant.
Maybe I will ask one question. Peter, maybe could you elaborate a little bit how Breakcat helped enable this work between Purdue, Burra, and Breakcat, and what's Breakcat's role, and maybe more broadly, what's Breakcat's role in terms of helping users and so on?
Sure thing. So this is an AWS service. It's still a service which is fairly new and early, and our customers are not large enterprise customers. Most of our customers are doing research, and so then they are usually not the most familiar with AWS, and so we help them get the account running. We help them, if it's credits that arrive to their account, then we help them use those credits. Often what happens is that the PI has an account, and then they want to add students to their account, so then they can work under the same environment. So there's a bunch of infrastructure work that we help them just on board. And in fact, that's not what I am or my team is doing, but there's a bunch of other teams attached to AWS in general who help people set up these things. So if this is intimidating, it's not an unusual situation, and we can help. So that's one part. The other part is what I'm doing. I'm an applied scientist in a team that is more focused on applications and engagements. So if you have an idea what you want to do, but you're not certain, shoot me an email. Or there's a bunch of feedback buttons everywhere on this. Like, tell us that you want to do something, and we are happy to discuss. Most of the time, we don't find a clear path, but once in a while, such as what we just showed, there is a pretty amazing work that we can do. So it's opportunistic at the moment. I really hope that my inbox will be flooded, and then we will work together.
Are there more questions for Peter? No, let's just thank Peter and Mr. Wagenstein. Yeah, okay.